Hello everybody and welcome to the geometry lesson on 4.4. It can be found on these pages. And here's your new vocab for this lesson. Make sure you understand those terms, those theorems, those postulates by the end. And here again is a reminder to use extra examples in your books when you are working on your assignment or the problems that are assigned from there. So let's get started with here exploring Angleside Angle. I have 4.3 up here from before. We already did this one, but kind of in the same way that we explored side, side, side to see if that was a way to prove triangles were congruent. Also in a similar method or a similar way was side angle side a way to prove triangles are congruent. We're going to see now if angle side angle is also a valid way to do that. So what am I saying here? I am saying that we have an angle, an included side, and an angle that's congruent to an angle, an included side, and an angle in a different triangle. So is there a way to make this triangle and this triangle different? Notice I don't have the triangle yet, but I'm going to maneuver it around so that I come up with some triangles here. So what's rigid here? What cannot change? This red angle cannot change. This green angle cannot change, and the blue side cannot change. Notice angle, side, in between angles, included side, in other words, and the angle. Can I change this red line here? Yes, this is allowed. So notice, so I can't go up like this. Then I've just changed the angle right here. This is no longer the same angle measurement. So I have to keep this red line just touching that red angle arc mark right there. Otherwise, it doesn't work. So I'm going to show you how this is going to work right there. Now it's just touching. So I'm going to extend this out. And I'm going to do the same thing with this green part. So notice the green line, the segment, that can change, but the angle itself cannot. So I'll extend that out here, and I gotta change that a little bit. I want to use this one. Okay, so can I do this? No, I can't, because that means the angle just changed right here. Can I do this? No, and then the angle's too small. The angle has to stay the same size. So I had made it so it would just be touching there, so just like that, and it looks like that's the only triangle I can make. If I continued with that segment, it's not going to be a triangle anymore. It's just going to have this extra portion. So let's see if we got the same thing going on over here. So this one, same sort of thing. I can extend the side right here. I think that's definitely not the way I want to do that. Let's undo that. So let's see what we got here. This is kind of rotated around a little funny. So I can take this and I can extend it this way. But remember, I can't change that angle, so I can't go this way. That's not going to be allowed. I can't go this way. That's not allowed either. So I can extend it up this way, though. I want to make sure it's just touching that red angle mark. Okay, and now I'm going to do the same thing with the green parts. I can extend this angle in just a moment. I can extend this side right here. And it's got to be just touching that angle arc marks again, because the angle can't change. So it looks like in this one I made my red line or my red segment just a little too big, so I need to pull that back. Now I've got a vertex right there. And so let's see if this is any different. You'll notice there's slight little variations here. Maybe I can fix those right now. So take that, and I'll do that here, and I'll take this and I'll move that down there a little bit. Let's see if I can drag this out just a little bit more. Okay, so that looks a little better to me. So I'm going to take this triangle now, and I'm going to see if this is the same as that. Is this any different? Was it possible? I sure tried my best to make this one different than this one. I did copy and paste the original thing, and I kind of flipped it around and rotated a bunch. But let's see. Let's see if I can move this over here and have exactly the same thing. So I notice, well, I got to flip this around, it looks like. So let me mirror or flip this in one of the axes. I'll go with the y-axis, and then I'm going to rotate it around here. So to me, even before I move it over here, it sure looked like it was going to be congruent here. And notice, it looks like, you notice how this, this is a little wider, the angle's a little wider here, so I would say that would be more like that. So let's move that in a little bit. There's some slight variations here. But now let's see if I can grab this a second. So now I've got the whole thing here, and if I move this up here, again we have some slight variations here with the way I had done things, or the way things were connected somewhat imperfectly. So I paused for just a moment there just to make sure I adjusted those variations so that it would be more accurate. And as you can see here, it's not absolutely perfect, but that sure to me looks like that first one was congruent to the second one. And so we could do this all day long if we wanted to. We could try all different kind of angle side angle variations, and we could try to flip stuff and move it around, but in the end you're always going to get a triangle here that matches up exactly, that's congruent to a triangle over here. So angle side angle, is it a congruence postulate or theorem for triangles? If you have an angle, included side, and an angle in one triangle, does it have to match up? If it has that same sort of relationship in the other triangle, do they have to be congruent? Yes, they do. They do. Okay, so let's work this or write this out. So now at this point, before I wasn't having you draw that. If you drew anything or what I was doing there, erase that, but definitely at this point now we're going to start drawing some stuff. Whoa, I didn't want to change the colors and all that. There we go. So I just want to put a mark right here. So I was saying this angle, the included side, and this angle had to be congruent to another triangle over here. This angle, the congruent side, and the angle over here, the included side, in other words. So let's write this down at this point. So we have the theorem, or this is actually a postulate. So angle side angle, we can write ASA. If you wanted to write out the whole words angle side and angle, you could do that, but I think it's not necessary. This is a congruence postulate. I'm not going to make you memorize that this is a postulate and the other one, or the other ones are theorems or something like that, but this is a congruence postulate. So this is just something we are assuming is true. This is postulate 21 in your books. So here's angle side angle. So have these pictures down. Copy of a picture here, copy that matches up over here. Write this down for me too. Angle side angle, we say this, that if two angles and the included side, so it's the side included in between the two angles and the included side of one triangle are congruent to two angles and the included side of another triangles are congruent. Okay, so we've got side, side, side. We've got side, angle, side, and now we have angle, side, angle. Let's see if there's another one. So we're going to test this out now. Angle, angle, side. Is this another congruence relationship that always holds true in triangles? So you'll notice I have an angle, another angle here, and then this side. This blue side is going to be rigid, just like it was for us over here. I did not change the length of the blue side, but I did adjust the length of the green and the red sides. So I'm going to be doing the same thing in this one. I'm not going to change the blue side, but I can adjust the red and the green sides to make it how I need to make it to make a triangle. Okay, to save ourselves some time here with the lecture, I'm going to just kind of move some stuff around, and I'll show you what I got after I've maneuvered some things around a little bit. Okay, so notice what I did here first. I just moved this angle into place so that now if I extend this side out and connect it there, okay, so now this is a completed side now. You could say the red and the green came together to form this side. And notice or remember that this blue side cannot change the length. I can change the green and the red sides. I can't change the green and the red angles that I've drawn because that's my angle, and now a non-included side. Notice the difference between angle, angle side and angle, side, angle. That's what I'm saying. Here it was the included side, the side between the two angles. Here I'm saying it's the non-included side or a non-included side. I could have ended up using this one. That would also be a non-included side. But I'm just saying we're going to use this one, so that really doesn't make difference. Let me extend this one now, and let's see what we got here. Let me make some adjustments here. So this, I'm going to pull that way. Notice I didn't change the angle, so I would say this would go just so it's touching there. I'd say right there. Okay, that blue side can't change, so I just need to move that so it connects right there. So it looks like we are pretty darn close here. So right there. So I've basically got a triangle right there. But I do feel like I need to adjust this just a little bit. So I feel like I need to move in the green part a little bit here so that it does actually touch the blue part. Okay, because I can't adjust that blue side. That's not allowed. Nope. So now let's pull this green side back a little bit. Alright, and I want to make the angle touch just a little better here too. Okay, and now just adjust this one a little bit more. Again, I can't change that blue side. That looks a lot better to me. So let's do the same thing over here with that. Okay, so I've adjusted this. I'm hoping that this will line up a little bit better. I had this one, oops, I had this one done horizontally. There we go. So now if I connected that or kept that going, looks like I should take this. Let me adjust that a second. Okay, so made some minor adjustments there just so it's easier to maneuver, but notice again I didn't change the angle size. I didn't change the angle size here. I just have these sides here in such a way that they're easier to maneuver about. Okay, so I'd say that is pretty darn good right there. That way the side is actually connected here, so we have a whole side here, and I'm going to take this now and move it up here. Notice can't change the angle. Got to keep that consistent, and so that looks much nicer. So let me take this now and I'll copy this, or I'll just move this rather. I'm going to move it over here and see if this matches up. I may have to make some slight corrections to the way I had done things here. Let me flip that over a second. Flip it in the y-axis again. I'm going to rotate it. And notice that's something that's allowed if you're making things out of paper or using toothpicks or something like that to test this yourself. You can kind of see it works out perfectly here. So notice, yeah, that's pretty darn close to me. Notice I didn't have absolutely perfect things coming together like that because there were some slight variations in the way that things connected here when I was doing that. But if you look at that, I hope you can tell that, yeah, that's congruent to that. So both these triangles, you could do the same sort of thing here with this all day long. If you had infinite time, you could just keep going and keep trying to make different triangles and triangles, and you would never succeed because it's not possible. If you have angle, and an included side, or non-included side, excuse me, matching up with an angle, and non-included side in another triangle, they're always going to match up. So at this point, just like before, I want you to draw the picture. So draw this, now that we've maneuvered it around, draw this picture, put that marking on there. So draw a picture that looks like this, draw a picture that looks like this, and we've got what we need for this one. So this is our other congruency relationship. This one's a theorem, so this one the book actually proves, or you prove in an exercise. I don't quite remember if you use this one as an exercise or if the book proves it itself. So we can take this. This is theorem 4.5. So only the fifth theorem that we have in this chapter so far. But theorem 4.5. What's it say? Well, it's very similar to what we just said over here, but now it's if two angles and the non-included side of one triangle are congruent to two angles and the non-included side. So let's just write that down. If two angles and or I should probably even say and a non-included side, because there's actually two. This one and this one are not included. So I'll say if two included, or if two angles and a non-included side in one triangle are congruent to two angles, and a non-included side in another triangle the two triangles are congruent. So you should have these pictures down now, and you should have the theorem right here down as well. You didn't have to write exploring angle side up there if you're in my class. But hopefully that helped kind of to see how I can maneuver things around, but it's not possible to draw different triangles here. Not possible to draw different triangles here. 4.3 is 4.3, not possible to draw different triangles here. And likewise, not possible to draw different triangles here. You can flip them back around and rotate them back around, and you'll end up with the same triangle that you started with. So back to 4.4 here. Let's check out an example after we write down kind of just a synopsis of what we have so far. So we had the first one from 4.3 was that we learned about side, side, side. The second one, also from 4.3, was side, angle, side. The third one, we just learned about here, angle, side, angle. And the fourth one that we just learned about, it was angle, angle, side. Is there more? Are there more? That's to come later. Just hang on for now, okay? Thanks for your patience. So let's see what we got here. So here's some different examples of some different triangles. So this is just kind of to separate. This is like a 3-in-1 type example for example 1. Always make sure you write down the number with the example. It makes it easier to check your notes later on for me. So let's say we're starting with this. So starting with the stuff in blue. So draw two triangles like this, and we're also going to say that this is true. I'm going to tell you that this is true to start. So starting with things in blue, that one and that one are going to match up with this angle and this angle over here. So is this possible? Can we prove that these two triangles are congruent based on what's here? And remember, you can also sometimes prove extra things based on the picture. So all I have to start was an angle matched up with an angle, but doesn't it have to be true? Use a different color. If you're writing this in your notes, please use a different color for this, because I'm saying, well, this I could also say was true even though it wasn't drawn originally in the picture. I could also say that this matches up with this over there. Let me make that a little nicer looking. There we go. So these angles also being congruent by vertical angles, so we could say that's true. But can we prove any of the sides are matching up based on what's here? Well, I don't see anything that lets us say that. I didn't tell you that something was the midpoint. There's no congruency tick marks on here. So in this case, was this one of our four things so far? Is angle one of our four things that we have? And angle, does that actually work? Well, couldn't I just make this triangle right there? Could I just like expand it, make it bigger and bigger and bigger? And it's not going to change the angle size, it's just going to change the side length. So angle, maybe we'll explore that a little bit later, a little bit more later on, but is this a congruency statement that we could say is true? Does this triangle have to match up with this one? We would have to say no. And if we had to give a reason for that, we would say there is no angle. Or we could say A is not a congruency postulate or theorem. So I'll put post for postulate, THM for theorem. So angle A, that angle does not work. Angle A. Anyway, so this one, how about this one? Let me add some stuff in here. So this is what I'm saying is given to start. This angle is going to match up with this angle down here. This one's going to match up with this one down here. And that's it initially that I'm going to tell you. So you may look at that and say, well, I don't see anything that will let me say that those two angles are congruent, and all I've got is angle, and so no, Mr. Wagner, That's not possible. But hold on. Hold the phone. Hold your horses. Hold the phone. Hold on a second. What about this one right here? Doesn't that have to be, or isn't it the same side in each triangle? Don't they share that side in common? So if I'm talking about this triangle versus this triangle, it's exactly the same in both. Reflexive property tells you that that would be congruent to itself. It's in both triangles. So, do you have all you need? Well, I see angle, side, angle. Angle, included side in the angle. It's not one of these two sides, so it's an included side. Angle, side, angle, matching up with angle, side, angle. So what I say, in this case, I would say yes. Why is that true? All you have to say is by angle, side, angle. Okay, so we saw one now that does actually work. And let's see if we have a third one that works or doesn't work. So is this going to be yes or no? Let's draw some things in here. So let's say that this and this. That's true to start, so that angle matches up with that one. And I also have this side matching up with this side here. So by that, I'm not saying that this side matches up with this side. I'm saying this is kind of like its own example within an example right here. So what would you say? Is this going to be true? Well, again, you look at that, you only have two pieces of information, and you might initially say, no, I don't think so, because angle side doesn't work, or side angle, that doesn't work. But again, hold on. Can we say something else? Just based on the picture, is there anything else that has to be true? Oh, okay, I got you, just like up here. You got that, has to match up with that down there. So that was vertical angles right there and right there. That is a horrible looking arc mark. A horrible set of arc marks right there. Man, that's still, but you get the point. Anyway, so we have this triangle now and this triangle. Do you have one of these four things? Do you have one of these things right here? I look at that and I say, I sure do. I see an angle, and then a non-included side. It's not the side in between them, but it's a side that's not included in between them. Angle, angle, side, matching up with an angle, angle, and a side. So this one, I would say yes, and this one's by angle, angle, side. The non-included side is the congruent part. So there is quick examples of three different variations on triangles there. Are we going to do a lot of these? Is this going to be on a quiz or a test? You bet it is. So being able to do stuff like this, very important to being successful in this chapter. But let's move on to a second example here. And let's also draw in some things on this one. So I'm going to go back to black. And now I'm going to say that black, the stuff in black, is the stuff that I'm starting with originally. So let's draw this in. Oh, I remember what that means. That means, I hope you do too, that means that it is parallel. So this, if I continued it all the way on forever and ever, that means they would never touch. So that this one and this one would never touch. And I'm also going to give you some labels here for the points. So this is going to be M, an A, an R, a T, and a Y right there. Okay, so M, A, R, T, and Y. Anybody know a movie? It's got a guy named Marty in it. Yes? No? No? How about this guy? Does this guy look familiar? It's an older movie, but it's a classic. It's one that a lot of people have seen, even your age, I would hope. What movie is that? That is Back to the Future. Okay, so Back to the Future, great movie from the 80s. I love that movie. This is Marty McFly right here. McFly! Hello, McFly! Anybody home? Sure, I'm home. Come back. There we go. Alright, and let's tell you some given stuff and what we want to prove. So for this one, instead of rewriting given things, I'm going to say see below. I know I've said see above, and then I would write the stuff initially here, but let's say see below for this one. And now to prove, I'm going to try to prove that triangle MAR is congruent to triangle MYT. That's the congruence relationship. So notice I'm saying M, then to A, then to R. Does it match up in the same way as M, Y, T. I think I need to check that a second. Yeah, glad I double checked that. I wrote this down, wrote the letters down the opposite way that I wanted to. So let's change that to M. Let's change that to, I didn't change it at all. This should be, there we go, Y and T. So M-A-R-M-Y-T. That looks like a correct possible congruence relationship. I would not be able to say that A matches up with T. That was what's wrong with that. So yeah, I made that mistake on purpose, of course. I always make mistakes on purpose just to make a point. Right, Mr. Wagner. But hey, you know what? I was able to make a good point from it. So let's draw, we are going to do a proof here. Let's draw in statements, or write in statements and reasons in here. So let's start off with what we always start off with, the given. So I'm going to write down my reason as given. What's given? Well, in the picture I can tell that AR, or segment AR, is parallel to segment YT. I'm going to say that's true. And I'm also going to tell you that this is true. This is not included in the picture, but I'm going to say that M is the midpoint of AY. M is the midpoint of segment AY. So based on that, now take out a different color. Please use a different color as you add different things to the picture. So the black stuff was there originally, or your stuff in pencil, since you should be using pencil, right? Right. I always use pencil in class, Mr. Reagan, all the time, like I'm supposed to. I'm a good child. I'm a good student. Good. I'm glad to hear that. Okay. So let's also now, based on what we just said here, let's add some stuff to the picture up here. If M is the midpoint of AY, can't we logically then say that this would have to be congruent to this? Well, sure we can. That's what midpoint means. That's, in other words, the what of midpoint? Starts with a D. What did you say? It's the what? It's the definition. Yes, the definition of midpoint. Okay, so it's the definition of midpoint is my reason. I'll abbreviate midpoint like that. That's the reason I could say that AM is congruent to YM. Say it like that. Could I say AM is congruent to MY? Sure, that would be the same thing. So I could flip-flop the order of those letters in step 2. What else can I say? Looking at the picture, because side to side, that's not enough. I need some angles, or I need all 3 sides. I did not tell you M was the midpoint of RT, so I couldn't put marks there and there. But because these are parallel, okay, let's go back to stuff about maybe alternate exterior, interior, corresponding, things like that. Do you remember stuff about transversals? I hope so. So we're going to look at this right here being the transversal for these 2 parallel lines. Well, wouldn't that be right here and right here? Aren't those alternate interior angles? Yeah, sure. How about, well, this one looks like it's 90 degrees. Can I assume that's true though? No. But I can say that here's the transversal now here with this parallel line and this parallel line. So if that's true, these also would be alternate interior angles. This one and this one right there. So I have 2 pairs of alternate interior angles being congruent. So let's write down for step 3, I could say that angle, well, this one I can just use 1 letter actually, because there's only 1 angle coming out of there. So I'm going to make life simpler on us and say that angle R is congruent to angle T, and I can also say that angle A is congruent to angle Y. Could I have used 3 letters and said, for instance, like ARM is congruent to YTM? Would that work? Sure would. But because there's only 1 angle at T and 1 angle at each of these other letters, I can use the easier way to write angles. And why would this be true? Well, we said again, transversal alternate interior angles for each transversal there. So I would just say AIA. Could I actually prove something else was true here? So could I do that in this picture? Could I? Yes, I could. Could I prove that vertical angles right here and right here are congruent? I sure could. So let's talk about that later. But I actually have, if I did that, I would basically be doing an extra step that's unnecessary. So let's just finish the proof off since we have enough to prove it, and then I will kind of reiterate what I was saying there, restate it, what I was saying there. So what do I have here? I can say that triangle ARM, or MAR, let's write it the way that they had it there. So triangle MAR is congruent to triangle MYT. So why would this be true? Well, we've got angle, angle, side, non-included side. So angle, angle, and non-included side matching up with an angle, and a non-included side. So I would say angle, angle, side would be my reason for finishing the proof. So I would say for this part, my further explanation, maybe just listen to this, or if you want to write a note off to the side that this would have also worked, I will erase this in a second. But I'm saying this would also have been a possible thing to prove. Vertical angles would tell you that. So if you had maybe you just saw that R was congruent to T, but you didn't see that A was congruent to Y by alternate interior angles. You could have used that in the definition of midpoint. You could have used this one, and this one to also have said angle, angle, side. If you notice that A was congruent to Y, but not R and T, then I would have angle, side, angle, and angle, side, angle. So are there different ways sometimes to prove things? Yeah, sometimes there's different logical things that you can say based on the picture or based on what's given, and you can sometimes prove what you need to in a different way than somebody else did. But it has to be logical, has to follow from what's actually here given in the picture or given in your information. So I'm going to erase that yellow stuff, and I'm going to say that we did it the way that's already down there. But that was an alternate way to prove this one. You could have used vertical angles in there as well. So let's do a final proof for now here. And so we mentioned Marty McFly, we mentioned the movie Back to the Future. What is that all about? I've got some other pictures over there. We'll bring those up in just a second. But let's say I have T, I, M, and E. Time. And that is, for right now, that's all I'm going to tell you. I'm not going to put any marks on the picture. We may be able to add some marks as we go. But time, what is Back to the Future all about? Well, it's about time travel, and they travel in this DeLorean time machine, a pretty awesome car, wouldn't you say? I want a car that has doors that open up like that. Pretty sweet. What's another movie that involves time travel? Oh, do you remember that scene from Napoleon Dynamite? Yeah, Napoleon, don't buy time machines off the internet. Not a good idea at all. So let's go from here and tell you what's given and tell you what you have to prove. So let's say given this one, I'm going to do the same sort of thing as I did last time, just so we can save ourselves some writing. I'll just say see below. We'll put the given stuff in the proof, and then what do we want to prove? Well, I look at that. A congruence relationship would be TIM. So triangle TIM. How would that match up with the other triangle? It looks like to me it should be TIM, and the similar order down here would be TEM. So triangle TEM. So let's work on a two-column proof now. So let me bring this back out, and let's make our statements and reasons columns. And let's put an S here, statements, and R over here for my reasons. What's given? So what is given to start? I didn't say anything in the picture really, but this is what I'm going to tell you is true. I'm going to tell you that WZ segment, well, I used different letters originally, so I'm going to adjust this. I wanted to use time instead of what I had before, so I'm going to say MT rather, segment MT bisects two different angles. I'm going to say it bisects angle IME, and it also bisects angle ITE. So I'm going to going to tell you that that is given. Okay, so let's start with that. What would that allow us to do on the picture? Okay, different color time. Take out your different color. This is what's originally there. What can we add to the picture? What else can I put in here? So MT bisects these two angles. So let's start with IME. That's the first one I wrote. Well, if it bisects, couldn't I say that that is congruent to that? That's what bisector means. That's what the definition of an angle bisector is. So that's what's going to go over here. The definition of angle bisector. Based on that definition, I can say that that and that are congruent. I could also say that this angle right here is congruent to this angle right here. So those two angles are also congruent. And so let's write down the appropriate things here. Here, can I use just one letter? No, I've got multiple angles starting here out at M. So I have to say, I would say something like this. Angle IMT is congruent to angle EMT. And I could also say over here, this one, angle ITM is congruent to angle ETM. Both of those being by the definition of angle bisector. So I've got angle, any side? Oh man. Oh, can we prove this one? Did I try to trick you? Hold on again. Look right here. Okay, so this triangle, doesn't it share side MT with this triangle right here? Yeah. So isn't this side the same in each one? Couldn't I do something like this in a sense and say, okay, MT matches up with MT over here. In other words, let's write this down. Again, it looks kind of funny to me when I write this down, but it's true that MT is congruent to itself. MT is congruent to MT, and I write that because it's in both triangles. It's part of both triangles. So MT is congruent to MT. And what's the reason for that? Well, that's when something equals or is congruent to itself, that's when we use the reflexive property. So this is the reflexive property right here. And so now, do I have enough to prove that the triangles are congruent? Now I got it. I've got angle, an included side, and an angle matching up with an angle, an included side, and an angle in the other triangle. So now I can say that triangle TIM is congruent to triangle TEM, T-E-M. Triangle TIM and TEM are congruent to each other. And the reason for that, remember, angle, side, angle is what we had just said. So ASA, do I have to have you write? This one was the theorem. Do I have to have you write theorem after that? This one was the postulate. Sorry, do I have to have you write postulate after that? No. You can just say angle, side, angle. So I didn't have any side, 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 or side, angle, side in this lesson, but could that also still hold true? Might you see that in this lesson and beyond? Yes. So this is what we got. This is the big thing to remember so far. These are the 4 ways to prove triangles are congruent. You can remember that. There might be some more. We are still going to talk about if there are any more that we can say prove triangles are congruent. But for now, that's all we got. So you can use these 4. Hopefully you found that helpful, and hopefully the lesson goes well for you. Let me know if you have any questions in class.